So I don't know who's responsible here for the schedule, but to put the boring robotic guy after Laura London, it seems to be completely unfair to me. The only experience that I have that was about the same was when I was in Malaysia and they asked, oh, do you want to sing some karaoke? And I said, oh yeah, sure, I can sing some karaoke. And then the guy asked me, I should have known something is wrong because they asked me if I had done my sound check and I'd never even, I wouldn't even know what to do. And then the guy in front of me was the winner of the Malaysian Idol show. And then let's give it up for Professor Jacky. So, in that spirit, let me tell you about my work with robots and why I think they're important. And obviously, I don't have the focus that I need. Let's try. So my research is on humanoid robots. I'm interested in robotics because I want to understand how the human brain works, and I want to look at humanoid robots and the specific features and research challenges that we need to overcome in order to make them useful. Walking on two legs is difficult. When we started this work in 2002, nobody really could do it. Now it's not a big challenge on a carpet, on a flat surface. We're trying to move into uneven terrain, gravel roads, path through the forest, and also push recovery. So if you push a robot, it doesn't fall over. Complex motion planning, which is something that humans are very good at, but robots are still very bad at it. For example, my door in my office in Taiwan has two latches. So there's a doorknob that I need to turn and another spring latch. And I need to turn both of them for the door to open, which is not a problem. And if I tell that to a graduate student in a week, he can implement an algorithm that will open the door for the robot. But when you carry a laptop, then that is a problem, right? Because how are you going to do that? So what I came up with is, when I open my door with a laptop now, I carry the laptop in one hand, I use the doorknob, twist it, use my knee to lock it, and then open the second spring latch. And the point is not that this is a good balancing act or anything like that. It's just that if I ask a student, how do you open a door, they would never come up with that particular solution. But many scenarios in the real world, we need to plan new motions in order to achieve our goal in unforeseen circumstances. And then I'm also interested in human-robot interaction, being able to teach robot new tasks, things like that. And for many years now, I've been interested in robot competitions because I think the kind of robots that we want to build are robotic firemen. Okay, we want to do research on robot firemen. Then we could have a task. We say, okay, we put the building on fire, have a couple of fake victims in there, send in the robots, none of them come out. We don't really know now which ones are doing good research, which ones are doing bad research. So we need to have some intermediate steps. And I believe athletics and magic are excellent benchmark problems for robotics research. Now, I've talked to some of you, I had the pleasure already of talking to some of you during this day and yesterday during the show. And one thing that I sort of changed in the presentation overnight was that the perception of where AI currently is actually a little bit off the popular perception. So when I talk about robot and artificial intelligence and what the challenges are, then a lot of people think the high-level reasoning is the problem, right? When we started AI research, we thought playing chess, playing Go, games like that would be the most difficult thing, the task that would require the most intelligence, and that where we should spend the most of our effort on. So early research was all in these domains, but you may know playing chess has been solved since 1996 when Deep Blue beat Kasparov. Go has fallen to the computers in 2016 when Google's AlphaGo system beat Lee from Korea, and now really no human can measure up to the computers in playing these kind of games. In truth, however, is that this is only a very small part of human problem solving. It's a kind of problem solving where humans are really bad at compared to a computer. But the things that we take for granted are actually much harder. So I want to ask two volunteers quickly to come down. You two there. This is not a magic trick, so. Just to give you an idea of what the problem is that we're dealing with. If you lie down here in front of the stage, and you get him to stand up. I mean, just tell him.
Stand up.
Stand up. That's easy, right? There's no thinking. That wouldn't require any thought. Nobody gets a grant for doing it. If we do this without a robot, you lie down again. Then I can change your light. Okay, so now I speak Chinese, my robot doesn't understand Chinese. If I want you to stand up, what you can try now is, I need to control every muscle. I need to say exactly what position that muscle needs to move to. I need to specify exactly the velocity at which the muscles move for him to be able to stand up. So now try again. And I'll let you use just the joint modules. Like, you don't need to look every muscle fiber. So just see how, if you can make him stand up.
Like pulling him up.
No. Like, okay, move your arms like this. Move your legs like this. Move your feet like this.
Okay, yeah, bend your knees. No, that was stupid. Well, bend your arms. Push.
Which direction?
Downwards.
Which direction?
Perfect. Gosh, how would I do it? Bend over. Move your hands forward. Yes, we're getting there. We're getting there.
So I think people and what Moravec already identified in the 1960s, the things that you take for granted, the reasoning that you do subconsciously is much, much harder than any of the symbolic AI level that we're considering when we're talking about artificial intelligence. Now we have made great progress. If you followed the popular media, you will have heard about deep learning, machine learning, the vast improvements that we've done. But these systems are still extremely fragile, and you should be worried because a lot of them will make decisions that actually impact your life. In California right now, if you're sent to the court and for some crime, then the judge has some leeway in how long they're going to send you to prison. That is dependent on your the probability that you are likely to commit another crime. Yes, correct. And that score is calculated by an AI system. That's a network. Nobody knows what that actually calculates. Right? It's just a number that comes out of a computer. But they're extremely fragile. So you can see here, top machine learning system shows a picture of a panda, boom, 57.7% confidence, no problem. Now I show it this picture. The only difference between this picture and this picture is a very small amount of noise that is added. Now we can take the panda and convert it into a gibbon. Right? So here, now the computer is 99% sure that this is a gibbon. This is a panda. Okay? And you can tell the difference between those two. As a human, those are exactly the same pictures. I can do even better. I can make this into a gun if I want to. So all of a sudden there's a picture, then I can answer random noise. The judge will see a picture of you of a gun instead of your cat or a dog. And here for a stop sign, I can take that stop sign that's recognized by the computer system. Actually, this will now be recognized as 45 miles per hour speed limit sign. Right? And no human would make that mistake. So I have to move a little bit faster. We have different robots, humanoid robots that we build in different sizes. And for me, robustness is a very crucial feature for artificial intelligence and also for humanoid robots, the ability to solve many different tasks, not just a single task. Because if you want to have a robot that delivers mail in an office, then you build something with wheels and a little screen will work much more efficiently, much cheaper, much more robustly than a humanoid robot. Humanoid robot only makes sense if you want to have a robot that can do the dishes and wash the windows and deliver mail and walk upstairs. And that's sort of similar to the animal kingdom. Humans are not actually the best at anything. We can't run as fast as a cheetah, we can't swim as well as a dolphin, can't climb as well as a monkey, but we're in the top 5 in anything, which sort of makes us special. So we came up first with the robot competition for athletes, where we have robots competing in, for example, weightlifting. So this is not just a challenge for the shoulder servos, but it's actually a balancing problem. The idea is that the robot needs to be able to walk, both with the center of mass low and the center of mass high. So here you can see our robots performing the weightlifting competition, needs to walk up, recognize the bar. And so there is an international competition every year. Before COVID, we had about 1,200 participants. And they all build robots to solve these kind of challenge problems. So first, no weight. Now we have a weight. Center of mass is much lower now, so the robot needs to compensate, needs to navigate, 1 foot touching the lift line, now has to lift the weight above the head, and then keep walking. So now the center of mass is much higher. Now this is actually my team. We're doing okay in that event, not world class. The world record is actually 90 discs. And there's also a sprint event. Sprint is interesting because, and I promise I'll only show the first 20 seconds of this. You think walking forward, if you walk towards this sign on the wall there, then the algorithm is very straightforward. Just walk, and if I'm off, I turn toward it, then I keep walking, and I stay within my lane. But just walking backward makes it a lot harder, because if I'm off, and I turn towards the sign and keep walking backward, now I'll walk out of bounds, so I need to have a line reference instead of a point reference. So there they go, just like the Olympics. 3 meters forward, then they need to recognize the position, then they need to walk backwards. The nice thing about doing robot sports is that we get very good quantitative results. For example, the world record 5 years ago was 48 seconds, now it's 23 seconds. And anytime something goes wrong, they have to bring back the robot and start from scratch. Then we have a Spartan race. This was the first time the robot climbed a rope. Marathon outdoors, which makes the vision a lot harder. Triple jump, basketball, archery. I'll skip the archery video. Now, I got interested in robot magic because I believe in the approaches so far in AI. We have very much ignored the importance of attention. And I think attention is crucially important for human reasoning. If you look at this particular picture here, for example, then whether you see an old grandma looking to the left or a young lady looking away from you depends on what your brain sees first. if you see that line there as part of the mouse, then you will see an old grandma. And if it's part of a chain, a necklace, then you will see a young lady. Okay. Then let me just finish off with one video for the magic, so actually I can do the magic. So we've run the magic competition. Let's do this one. Actually, no, let's do it. So here's a magic trick that we're doing. The presentation is actually all online, so you can watch it yourself. Hide the coin behind the back. And now they're always trying to figure out which hand the coin is in. And so magic-wise, this is pretty easy. Now it asks you to cross the hands. And most people will put the coin, a couple of features that we use, but most people will put the coin underneath. So we just go with that. You can see what the robot sees. And again, one of the issues that we have is that one of the problems that we had is that it's easy to write computer vision algorithms that can tell you that the arms are crossed, but figuring out which arm is on top is really, really hard. And very last one, I'll skip through it quickly.
Be very happy to feature these videos. It's on our site.
Sure, yeah, we can do that too. This one is a nail magic trick where you have the nail and the hand and it goes down. And the funniest part about it is it works very well because it's in China, in Taiwan. And it's in Chinese where my student is talking. But what she's actually saying is that, oh, my professor, they wanted us to use deep learning to recognize where the coin is in the weight. And it's all too hard. It never really worked. So we always put it in the middle. So please just make sure you don't pick the spike in the middle. And they say that in Chinese, so then everybody's laughing because I don't speak Chinese. Everything okay? Yeah, everything okay.
Please place the nail inside the last bracket.
And then the magic trick performs. So, but I think I overran your patience. I'll let you watch the video online then if you want to, if we're really out of time now.
Thank you very much, sir.